Okay, this is section 4.3. We're going to be discussing mass and Newton's second law. So the inertial properties of an object are characterized by its mass. The acceleration of an object under the action of a given set of forces is directly proportional to the vector sum of the forces and inversely proportional to the mass of the object. Basically, what that means is if you take this particular equation, divide by m on both sides, that's the acceleration is equal to the force divided by the mass. So the relationship is Newton's second law. The sum of all the forces acting on an object is going to be the same as the mass times the acceleration, whatever direction magnitude that happens to take. If you break it down into components, then you have the resultant for f of x, the forces in the x direction, and the forces in the y direction. So let's say you have an object here of mass m, you have force 2 being pulled up this way, you have force 1 being pulled this way. This is the resultant. This picture is going to get kind of old by the end of chapter 4, but it helps. This resultant force is going to result in an acceleration, which is going to be the same thing as the force being applied divided by the mass. The mass is going to resist the change here that is being commanded by these forces. So that's why it's in the denominator. So let's take a look here at the section itself. So we have a constant force causes a constant acceleration. So we've got our device here, spring device, which is measuring the force. If the force is constantly being applied, then it's going to end up giving a constant acceleration. If you double the force, then the acceleration is also doubled. And you can get that from the formula that we had earlier. Force is equal to mass times acceleration. If you just put a 2 in for the F, then the acceleration is also going to be have a 2 with it as well. Having the force is going to have the acceleration. So we have another experiment here. We're going to give the object the same initial velocity as before, but with no force, the velocity is constant. With a constant force directed to the right, the acceleration is constant and to the right. When we reverse the direction of the force, we're going to find that the object moves more and more slowly to the right, and the direction of the acceleration is towards the left. And then we're going to conclude that the magnitude of the acceleration is proportional to that of the force, and the direction of the acceleration is the same as that of the force, regardless of the direction of the velocity. In other words, it doesn't matter what the velocity's direction is, the acceleration is going to end up changing that, or accelerating it, depending on which direction the force is being applied. So we've got a puck that's moving at a constant velocity this way. If we apply a constant force in the direction of the motion, it's going to cause a constant acceleration, which you can see here means that the velocity is going to change. It's going to get faster. Let's say that puck is moving this way, but we are trying to stop it. As we apply the force this way, the acceleration is going to point this way, which means the velocity is going to slow down in this direction and may eventually either come to a halt or point back that way. So as you see here, the acceleration is equal to the force divided by the mass. The SI unit is going to be the kilogram. We had discussed earlier exactly how that came about, but this is going to be something that we're going to use in order to compute the amount of force. And again, the mass is going to be the kilogram. Now, that's going to be something you're going to need to remember later on when we are discussing weight. Mass and weight aren't quite the same thing. The Newton is going to be 1 kilogram times 1 meter per second squared. That's our fundamental definition there. You need to remember that going forward. So we can also use equation of 4.5. Let's see if we can find that. to compare a particular mass with a standard mass and then be able to measure mass. So let's say we apply a constant force to an object that has a known mass, and we find an acceleration with this magnitude, as shown in figure 4.2 here. So we've got a known force causing an object with mass m1 to have an acceleration such as this. We then apply the same force to another object that has an unknown mass, and we find an acceleration with this magnitude. Then, since both have the same force being applied to it, then the mass of the first times the acceleration of the first is going to be the same as the mass of the second times the acceleration of the second. And if we arrange it such that we have the masses on one side and the accelerations on the other, you can see how they're related. So if we know the accelerations, we know the mass of the first one, we can compute the mass of the second. So we've got mass 1, resultant force. We determine what its acceleration is. We've got a mass 2. It's having the same force applied. We know what the acceleration is. If we add them together, we apply the same force, we can determine what the acceleration is. In vector form, the sum of the forces, the vector force, is going to be the same as the mass times the acceleration of all of that. And obviously, if the acceleration is going to be 0, then the net force is going to be 0. It's going to move at a constant velocity, which may be 0 or it may be non-zero. If you take a look at the resultant forces in each dimension, x or y, then the force of all of the x forces in the x direction is going to be equal to mass times the acceleration in that direction. Same thing with the y.